Well, that is a way of a calculation, and right now we have the real internet delays and routers. So how to have the measure? So in the following, we want to have the measure. All right. So how do real internet delay and loss looks like? Well, we can have the trace route program. And trace route program, we have the delay measurement from the source router to the destination. And how to do? We will have 3 packets. 3 probing packets. All right, and then we can follow the 3 probing packets to directly have the report. All right, so the 3 packets reach the router, and then router can get back to the previous one. So how to do this one? First of all, send 3 packets, and the 3 packets we call probes. And of course, the probe packet can go further, but reach the router, then return, send, return. And likewise, we can have these. Go to the next one and return, and likewise, and so that we can have the real internet delay, and also possibly we can have the loss. And in the following, we use this one. Transform the current. Actually, we have the current situation. gaia.cs.umass.edu. Use the transfer, and so that we want to measure from the current source to the destination. Destination at eurocom.it. Oh, sorry, .fr, France. All right, so here we have the scenario from UMass in United States to Eurocom in France. Wow. We have the routers from CS Gateway and border 1 to the others. All right, so the 3 report allow us to have first delay, second delay, and third delay. So 3 delay measurement from the from source to the current router and etc. So up now seems to be 111, 111, and to this one 655, because of some situation the scenario not the same for the 3 packets, so they don't have the same value. So not the same value is natural. So we have these. If we have these, how to have the average delay? Here the delay here in fact include 4 types of delay, and we want to have the average delay. How to have an average delay? All right. So this is a way to have the average delay further based on the current records. And we just follow the current slide. We may find, well, 12 and then jump to 100 because of the transoceanic link. So that's why we have 22 to 104, because it's a jump. So that's why we gotta have the reason transoceanic link. Transoceanic link, so that we have a large enough delay. And also we have a scenario like this. This one, asterisk means no response. Okay, no response. So we have the symbol here, but possibly even we don't have the measure, but later we may have the measure. Even some loss, but still we can get for some further routers. All right. So here, if we talk about loss, what what's the loss rate here? Loss rate here is right 3 packets and 3 loss. All right, so loss rate around the router is 100. But sometimes you just have one asterisk, but 2 you have the value. So what is the loss rate? Loss rate is 1/3 multiply 100. So here I just say, if you want to have the loss rate for the current 2 routers, it should be 100. Of course, you can have the other. So this is a way to have the real internet delays and real packet loads for the internet. All right, so this is a transfer allow you to have the repo, and you can try later. You want to have your measure from your PC to some destination, so they can have the similar repo. Okay, so this one that you have the real delay. Well, in the past, we don't know we may have the loads, and actually I use the previous one to that have the measurement of loads 100%. And here we have the further discussion about loads, packet loads. So we have Q. If we have more packets exceeding the current capacity, and then we will have loads because of this full Q. So that we will have a draw and so that loss. As for how to have the calculation of loss, you can try, for example, n packets. So n packet, first one, no loss, and second one, no loss. If we have some loss, number of loss packets over the total packet trial, and so that you can have the calculation of loss rate. All right, that's all. And how about throughput? Throughput here, we don't have the capacity to ask you consider the throughput. And we may have the different link capacity. And we use pipe. All right, so we use pipe. And here, pipe doesn't fill the low capacity and the high capacity. And if I will ask you to consider throughput, throughput here is rate at which bits transfer between the sender and receiver. And of course, we can have the instantaneous throughput or average throughput. But right now, we ask you consider the first one, instantaneous throughput. So how to have the throughput for the scenario like this? First of all, we have here you know it's a server. Server going to the link of the server, and then the router, and then going to the link to the destination. Well, if we consider the link capacity, so how to have the throughput? All right, so I think we have the pipe, because our pipe that feel how to have the throughput. So the pipe here, the capacity actually follow the rate at which bits transfer. So at which bit transfer. So here we have the current throughput using this. But going through this one, the same, even you have even larger capacity. So about the current throughput, this one. So throughput here, RS, and throughput here, RS again. Why? Because right? So I smaller, but previously you have the constrained throughput at RS, so you're gonna have an increased throughput even you have capacity RC for the client side. About the current label, is it okay? Throughput for first link is RS, second link only RS, not RC. Even RC is even larger value. So this is the first scenario. about this? Is it okay? All right, seems to be okay. So throughput, in fact, we can have the Chinese characters, all right? And we have the explanation, what it means. And we already have the definition about throughput previously. But if you don't know throughput, and I already have the keyword again. Well, in fact, we want to consider the old example. How about server capacity lower than capacity as a client side? Here, RS, and here, RS. So end-to-end, it should be RS. And this one is RS. However, change it to RC, but finally it's RC. About this is okay. And while we have a bottleneck here, and bottleneck here, that's also, this is a way to have the calculation of throughput. Which one is smaller? So if we have this, the operator like this. So this is the end-to-end. All right, so the current operator using minimum, and minimum allow you to have the answer. Okay, so this is the revision of throughput. Well, if we have these RS and RC, but assume we have 10 links here. All right, 10 links, so each one share R over 10. Because of this, so we have RC, RS, and R over 10. And it says in practice, RC and RS is often bottleneck. In practice, sometimes we have a lot of link connections share the link R. So it doesn't mean R over 10 is always larger than RC and RS. No, so that's why we need to have a minimum. And that's it. This is a throughput. And actually, you can check the Java activity to feel the interactive animation about throughput. So this one, 10 connection, thoroughly share the backbone bottleneck link. Why? And later in later chapter, we can already know TCP connection can fairly share this one. So because of this, so that's why 10 link, 10 connection. So we use R over 10 simply, and so that we have the actual derived link capacity R over 10 because we need to consider the individual connection. So that's why we have RS and RC, but for the cloud, we have R over 10 given 10 connections. So if we consider the current 10 connection example, we have R over 10. If you vary the number of connections to the other value, then for example, you have 20, just over 20. If you have other value, you just replace the value so they can have the link capacity of the cloud